Hello, good afternoon, everybody. So, welcome to today's Samvaad-Talk. This is the last talk in the theme on education and technology. Today's talk is by Professor Sujit, Kumar Chakrabarti, and Nikhila on automated evaluation of programming assignments. We'll have Professor Meenakshi D'Souza chairing this session. To briefly introduce Professor Meenakshi, she has been with IIIT Bangalore as a faculty member since 2010. She did her PhD at Math Science Institute at Chennai, and she has worked at Honeywell prior to joining IIITB. Her research interests are in formal verification of software design, model-based development, and physical access control. She is very passionate about diversity and inclusivity and accessibility issues related to IT. So welcome, Professor Meenakshi. The stage is yours.
Thank you. Thanks, Jaya. I may not have the introduction. The talk today is by Sujit and a research scholar from our lab, Nikhila. Sujit is her guide. So welcome everyone to this last session, as Jaya said, on the Samvaad-Talk on education and technology. So Sujit and Nikhila are going to talk to us about a research project that Nikhila is actively involved in related to automated evaluation of programming assignments. Before I hand it over to them, let me introduce Sujit and Nikhila, today's speakers, to all of you. So Sujit has been with us for the past 8 to 9 years as an associate professor at IIIT Bangalore. Works on several applied areas related to software engineering and software testing, programming languages. And the topic of today's talk is specifically on technology for education. Sujit is also involved in accessibility and inclusiveness. He's a part of the Center for Accessibility in Global South, which IIIT is active in. Sujit has made significant contributions in terms of implementation heavy projects, including open source and technology transfer to ABB. Sujit also has strong hobbies, as he says, including cartoons, blogging, and is a good singer too. It's also my pleasure to introduce Nikhila, whom I've known since her master's days. Nikhila did her MTech from Government Engineering College, Idukki, Kerala. And after a brief stint at IIT Palakkad, joined us as a PhD student and has been working under the supervision of Professor Sujit Kumar Chakrabarti. And her thesis is related to the area on automated evaluation of programming assignments. And Nikhila is also interested in all formal aspects of software engineering. So over to you, Nikhila and Sujit.
So today, Nikhila and I will be talking on the joint work we have been doing for the past several years on automated evaluation of programming assignments, which also happens to be the topic of her PhD dissertation. So let me start. So this is the overall outline. I think many of the other things you see in gray, no problem. So I'll give a slight introduction in the beginning just to set the context and the motivation of our work. And then the talk is divided into two main parts. The first part, I will talk about some engineering activities, some practice engineering and practice and experience related work that we have done. This is more or less my own solo work. So, but yeah. And then we will spend most of the time in the next 1 hour or so in discussing some research work that Nikhila and I have been doing along with many other students, which are all in the ambit of her PhD thesis. In that, we hope to be able to discuss 3 distinct pieces of work, time permitting. Otherwise, at least 2 of them we will definitely discuss. And finally, I will wrap up. So before we get into the flow of the conversation, let me place the credits to where they belong. Much of the work that we are going to discuss are owned by Nikhila, who is our PhD student and who is my co-speaker in this session. One of the pieces of work which I hope to be able to discuss today was done by a summer intern called Kapil Karla. He worked with us in the summer of 2018. He's now doing his post-graduation in CMU. An extremely brilliant student, made significant contributions. The other piece of work is by three of our current students, Arjun, Pratiksha, and Rahul, who are IM Tech students. I would also like to thank Professor Manish Gupta, who is our professor as well as now heads the Google AI Research Lab. He was actively involved in the former part of all the work that we have been doing in this project, and graciously sponsored Nikhila's work in the beginning years. Thereafter, Minro took over the financial part, and I must thank them also. And of course, a very significant contribution was done by, I would say, numerous students, TAs, and project students and interns who have worked temporarily on this project for shorter periods of time. I would also like to mention that my last Samvaad talk, which was in 2019, was on the same topic. In fact, it was titled exactly the same way, Automated Evaluation of Programming Assignments. But I would like to mention that it is not a repetition of that talk. Okay, even though you may see some of the slides being repeated, but much of the work that we are going to discuss has happened subsequently to that talk. Primarily because COVID-19 happened after that, and we all went online. Education went online. Evaluation and assessment went online. Everything went online, and that has brought this area of research suddenly to the center of attraction. What probably used to be somewhat like one of the many areas of research in computer science is now probably one of the central areas of research. Okay, so it assumes a very significantly increased importance in the current scenario. Also, from our side, much of the work that we had discussed 2 years ago were more in the idea phase. Those ideas bore fruits, and we had a bunch of research publications since then. And much of what we are going to discuss today are basically contents of those research publications. Yeah, so today's talk is basically 2019 plus results. Okay. Right. So why automated evaluation? Again, this is probably a slightly dated slide, because I think now I don't need this slide anymore. Everyone understands why we need automated evaluation. We have all the online learning platforms, and now all our learning platforms are online. Okay. That automatically opens doors to have very large increased sized classrooms, and now manual evaluation is completely out of the question, right? So we need to automate as much of our evaluation processes as possible. So there is no question that automated evaluation is not just an important area, but it is almost essential now. And of course, our primary motivation has been the introductory programming courses, particularly our IM Tech first year courses, right? And the size of the IM Tech batches has monotonically kept on increasing over the years. I mean, the last batch I taught was probably 150 students, which is a significant size. And if I give you the arithmetic, you would be surprised to know how much time it would take me to evaluate all the assignments and exam papers, programming assignments and exam papers, if I had not recourse to any kind of automation. It would probably have taken me about 1.5 semesters to or devoted time to just evaluate all the assignments that were turned in over the semester. So it is that much bulk of work, which includes 6 to 8 TAs, by the way. Okay, so and furthermore, manual evaluation is extremely error prone, labor intensive, and repetitive. It's quite boring, and therefore we would not like to do it if we have some automation. The requirements from automated evaluation are, of course, no points for guessing. We want it to be faster than human beings, much faster than human beings. But we also want them to scale to larger numbers, which means that it's not enough to be fast for small number of assignments, but they have to also scale well for larger numbers. We also expect some sort of objectivity, which means that the interpersonal relationships between the examiner and the examinee should not have any influence on what kind of marks the students get. And furthermore, once marks have been awarded, we also want some sort of explainability. That's a fashionable word today, so let me use that here also. We want some sort of explainability to how we did the marking. Right? So these are all the requirements, and if you will observe closely, you will often see that they tend to often conflict with each other. Okay, so if you want to be extremely transparent, you may have to have very, very explicit ways of evaluating everything, and that may compromise your ability to scale your evaluation process to large number of submissions. So what we have contributed are these two things. As I told you, this talk is divided into these two parts. I will primarily give a demo in the first 10 minutes, hopefully not more than that. In the first 10 minutes, I will give you a small demo of a system that I have been using for evaluating programming assignments in the Python course and other programming intensive courses that I have been teaching. And the remainder of the talk will be discussing our research findings in the same area, but with a completely different flavor. Okay, so let me discuss the system that I have been using in my day-to-day evaluation tasks. Basically, what I'm going to show you is a sort of test harness. Okay, however, it has many benefits which I will show you, and through the demo, hopefully that will become clearer. It has definitely helped me. There is no doubt about it. What would have taken me several weeks now gets done in a few seconds, and it has also, at least in my opinion and in the opinion of some of the brighter students that I have taught, it has led to more frequent and deeper formative assessment with shorter feedback cycle, and that has hopefully helped the students. Okay, so what is the workflow of this system? Basically, I or one of my TAs or some of my TAs create and publish the assignment, and while the students get busy solving that assignment, in parallel, we write the evaluation scripts, and then after those assignments are turned in, we do the evaluation, the automated evaluation. We share the results, which the students are able to review very deeply, very in great detail, and they are able to provide feedback, which we again incorporate into our scripts and rerun the scripts all over again. And then finally the results are published. So this particular part is where a lot of innovation has happened in the last couple of years. The other parts I had kind of discussed earlier too. So let me just give you a slight technical overview of what goes on in that system. Basically, as I told you, it's a test harness. It takes the submitted assignments and impinges some inputs to it. We get some sort of an output, which is compared with an expected output, and the result comes out as a pass or fail for that test case. Okay, so this is one test case, right? And then we run a fairly large number of test cases. I'll show you again, how many they turn out to be. And then some sort of weighted summation happens to compute the final marks of the student, okay, for a particular assignment. This is the overall thing that happens. Yeah, this is probably okay. This is how the whole system is architected, right? So you should start reading it from here. So this is the test case that I'm talking about. There are many such test cases. Each test case, so each question in your assignment, right? So there may be question 1, question 2, and so on. Each of these questions actually gives rise to one test suite of this kind. Okay. Each test suite in turn has several test cases ranging from, let's say, 5 to 10 to even 50 to 60 test cases per test suite. Okay. And then we eventually calculate some sort of an efficiency, out of 1 for each of these test suites, which again maps to each question, as I told you. And then we multiply that with some sort of a weightage for each of the questions, which gives the marks obtained in that particular question, and adding them gives me the final marks of the student. So there have been several advantages in using this script vis-a-vis web-based off-the-shelf systems like DOM Judge. Okay, and here are just to name a few. First of all, it's extremely simple to set up. It doesn't require any infrastructure. It's running on my computer, the evaluator's computer. It doesn't require me to be connected to any server. It's also simple to use for the very same reason. Everything is just mere scripts running on my computer. It's also fairly language independent. I have at least used the system for 2 different programming languages that I have been teaching. And the overall architecture and this thing seamlessly flows between programming languages. One of the very important advantages of this system is the data availability. That is, we have extensively used all the data generated through all this evaluation workflows over the last couple of years for our research. And that has been possible primarily because all the data was there with us all the time. It was not locked in any kind of gigantic system or Moodle or some such thing, from which is easy to use, but the moment you want to do something with the data which is there inside it, you may have to do something which is quite complicated. Okay. Another advantage was the transparency that we received in the process, in the sense that the students not only were able to see what inputs were given to the programs they had written, but how they were evaluated. So they had complete inside view to the test scripts. They could actually review them, find bugs if there were any, and report them back to me, which could be fixed in no time. And the whole thing worked quite seamlessly. And that's what I mean by the word crowdsourced debugging. So since my evaluation scripts are written in time pressure and all the software engineering issues, there are sometimes occasional bugs. But the moment I share them with a large number of students who are very eager to find bugs, which is a very good thing for testing, software testing, those few bugs that I may not have seen get discovered in no time and get reported eagerly to me. So I have been able to very effectively use our students for debugging my scripts, and that has resulted in my scripts becoming very stable and high quality, and they can be used for further further evaluation with little or no changes. And finally, one of the biggest rewards of doing this system has been teaching by learning. So for many of the students, in fact for most of them, this system that I have developed, as I told you, I share the entire script with them. This is the first non-trivial piece of software that they actually lay their eyes on. And many of them are actually able to see through its design and architecture and are quite fascinated by it. So I feel that the effort that has been put into developing this system has borne rich rewards, because it inspires the students. It actually shows them they are learning Python, and here is a piece of non-trivial uh, quote-unquote industrial strength software system that has been written in that programming language is quite inspiring for many of them. So that's what I call teaching by example. So these are all the advantages. So I would like to show you a demo. Let me just check how I'm doing with time. I'm doing very badly with time. So maybe I will quickly do the demo. I will not explain too much. But the objective of doing the demo is that I want to showcase it to prospective or current instructors to programming courses and seek feedback from them. Okay, so let me quickly do this demo. I don't expect to be able to go too much into detail because of time constraints. So let me just open this. This is a assignment sheet, okay, and it has got a bunch of questions. You don't need to go too much into details. All I'm trying to show you here is that there are a number of questions, and many of those questions do not lend themselves well to plain old testing. For example, I want the students to implement one particular function in terms of some other function. So here add and subtract have to be implemented in terms of increment and decrement. And there are many such examples in this this assignment. And the objective of showing you this is to point out the fact that plain old input output checking is not going to work when we want to evaluate such questions automatically, where the structure of the program is equally important as the function of the programs. So keep this in mind and see how it has been handled in our case, right? So what I will show you here is, so there are a bunch of questions, and if I go to this evaluation directory, you will see these Python files, uh, uh, these three in particular. So there are three programming questions in the assignment, and there is one test suite file corresponding to each one of them. Okay, so eval mathhops, eval matrices, and eval sop, these three files. Okay, I can run each of these test suites independently. So let me do it for you here. Right, so I just tested uh, one of the test suites, which means I'm individually testing one of the questions for one of the students. Okay, if I want to evaluate all of them, I can go ahead and evaluate all the questions. So by running this script, so it runs all the questions and it gives me a final marks for that particular student. Okay, if I want to evaluate one particular roll number, right? So all the submissions are, by the way, here. Okay, so there are about 10 roll numbers for which I have kept the submissions. So if I want to pick any one of them, I can pick that up. So I can say something like eval sh, let's say rn010. Okay, so it picks up that particular roll number and gives me the answer final values for that thing, that particular roll number. And now if I want to evaluate all of them, then I run this particular script, right? I just say eval all roll numbers, and then it runs all of them. Okay, takes a moment, but is otherwise quite fast. Right, so all the evaluation has been done, and the next step would be to send these things to the students, all the scripts. So for that, I run this particular script. Okay, so it runs, something happens. What results as a out of this is the following. So if I go to evaluated package, I will see that I have these files. Okay, these are all the test scripts and the submissions inclusive for all the students. They are emailed to all the students, again using an automated script. So the students get these tar zips, they open them up, run and see why they got what they got. If they have any doubts about the final results, they are allowed to open the script, debug, and often they find bugs which they report back to us, and then we are able to fix them and rerun the whole thing. So this is the entire workflow, the demo of it. Yeah, so that's the demo. Right, so that ends the demo part of it, and now we are ready to go on to the next part of the talk, which is going to discuss the research work that we have been doing. This includes 3 parts, as I had mentioned earlier. These 2 parts will be discussed by Nikhila, and if time remains, then I will briefly touch upon the 3rd part. So at this point, I will hand over the screen to Nikhila.
Okay, thank you, sir, for the detailed introduction of AEPA work. In this talk, I would like to present approach detection module of AEPA and the similarity, program similarity checking, which is the key part of approach detection and approach matching module. Okay, so this is the outline of my talk. I hope I can skip the introduction part and directly jump into the program similarity part. So in the program similarity part, we'll explain our most recent work that is presented in the AI/ML systems conference for checking the program similarity. This is a joint work with IIM Tech students, Arjun, Pradiksha, and Rahul Muralishankar. And the next part, and the approach detection part, would like to present our paper on discovering multiple design approaches that is presented in a symposium on applied computing. So I'm skipping on this introduction part, then directly move on to the program similarity. So the term program similarity defines the state of being similar. A program is similar with some other program. So according to the criteria that we have used to define similarity, there are different types of program similarity available. For example, if 2 programs performs the same task, So according here, the task is defines the term similar. So if those programs are considered to be functionally similar programs. So in the same way, there are other definitions are available for the program similarity. So mainly the authors in the paper, sources broadly classifies the program similarity in 4 different parts. Okay, the first one is textual similarity. In this case, after removing the white spaces and comments, the 2 code fragments are identical in their text. Then we call them are textually similar programs. We can see in these 2 examples. In the program 1 and program 2, both are identical in code. Then other category is lexical similarity. Here, if the code fragments are identical, irrespective of their identifier names, then we call them as lexically similar programs. And the third one is functional similarity. As I mentioned before, if 2 programs perform the same task, then we call them as functionally similar programs. That means for every input, both the program is supposed to perform the same task. That means for every input, both of them produce the same output. The fourth one is structural similarity or syntactical similarity. This is our main focus. We are working on the measuring the similarity part. In the structural similarity part, if 2 programs are structurally similar, then both of them are functionally similar, and those 2 programs should implement in the same method. Should be implemented in the same method. So we can see that these 2 programs are supposed to perform the task finding the product of 2 numbers. One is use the for loop and another is uses the while loop, but it doesn't matter. Both of them uses the iterative structure to perform the finding the product. Okay, so the program similarity helps us to finding the different group the student submissions into different groups based on their approaches. Approaches mean the solution strategy they are trying to solve the particular problem statement. So here, these 2 programs are implement the same functionality, but they have uses the different approaches. Okay, so when we classify this, when we try to group these programs, it will give 3 different groups. One should the first one group should get the solution which follows the recursive structure. Then another group should contains the implementation which uses the multiplication operator. Then another group will contain the iterative structure. So in this manner, we can distinguish the students' approaches based on their student solution based on their approaches. So we found that the structural similarity is helpful to find those kind of approaches. So this structural similarity thing we have used to find the approaches and the approach detection part. Okay. Then our goal is to measure program similarity. We measure the structural similarity. So in terms of concepts involved, measuring program similarity between codes is similar to the concept something involved in the plagiarism detection. So we are because of this reason, we are mainly focused on 3 major plagiarism detection tools as our reference work. The first one is measure of software similarity, which is the most popular tool based on the most popular tool which is used to measure the detect the plagiarism, which is based on the textual representation of the program. and it uses the winnowing algorithm to find the textual plagiarism. Then Codex as another tool, which is basically a source code search engine that allows users to search a source code repository using a query, which that query is also can be a source code snippet. And another tool is GPLAG, which is based on the program dependence graph. Then it finds the plagiarism by finding the isomorphism on the program dependence graph. So let me talk more about our contribution on measuring this structural similarity. This is the work we have presented in AI/ML systems. Okay, so in this work, we are mainly focusing on measuring the structural similarity. So we take the measuring the structural similarity, we uses the abstract syntax tree as the basic structure for analysis and computation, because ASTs can capture the structural features of the code and represent it in a hierarchical manner. So first, let me explain the method using the steps that involved in the algorithm. First, we generate AST for the both programs P1 and P2. Then we have to do some pre-processing on that AST, because pre-processing means remove the comments, white spaces, and modifications in identifier names. Then modification means change the all the identifier names into constant character, because all these comments, white spaces, and identifier does not contribute much on the structural similarity. So we have to avoid those and need to handle this changes in statement order. For example, if in the first case, this A equal to 5, B equal to 10 is the order in the program P1, and in the P2, B equal to 10, A equal to 5 is the order. Then this order change is not much, do not contribute much on the structural similarity. So we have to handle this as well. So for doing this and measuring the program similarity, first we traverse the AST for both programs and extract all the nodes. Then along with extract all the nodes along with their subtrees. These extracted subtrees are then stored into 3 different lists, which is level 0, level 1, and level 2 for both programs. We can this level 1, level 0, and level 2 list are nothing but the tree list representation of the tree list. From this example, we can see that this is the level 0, which represents the entire tree. Then the level 2, level 1 as the forms the child nodes of the level 0, then and level 2, and so on. So we first we extract this list, then generate the fingerprints on this 6th list using winnowing with parameters k equal to 13 and t equal to 17. This means the generate the fingerprints means nothing but divide the list into k grams, hashing all these k grams and selecting some particular k grams to represent the list for comparison. So here that k means 13, and t is the guaranteed threshold, which represents the shortest match that we are guaranteed to detect. So the values are selected after doing the several experiments. Then we calculate cosine similarity between P1 and P2 for each levels, which is C0, C1, and C2, which is corresponding to the level 0, level 1, and level 2. Then we compute the cosine, AST similarity with weights W0, W1, and W2. The weights represents the contribution of each level in the overall similarity score. These values are also finalized after performing the several experiments. Then we have also incorporated a normalization factor called construct normalization to increase the weightage given to the construct used in the programs. Here, construct means the various control flow statements such as loops, conditional statements. So this is the formula for calculating the construct normalization score. So A is the number of construct present in the program 1 and B is the number of construct present in the program 2. Then the overall similarity score is calculated as the weighted sum of normalization score and AST similarity score. Then we observed that the scores obtained from the method described so far have the strong positive correlation with the manual ground truth values. That is, the ground truth value is a monotonically increasing function of similarity score obtained using the proposed method. But these are not always equal or directly proportional to each other. So to provide final score, we use a scale. We scale the score to get the proposed method using a scaling function. We use a supervised machine learning method to learn the relationship between the estimated similarity and the ground truth value. This scaling function, which are used to scale the system and evaluate the arbitrarily large number of submissions. We approximate the nonlinear relationship between this similarity scores using a piecewise learning model. The training set is divided into 3 subsets, which equally in size, with ranges from the 0 to tau 1, tau 1 to tau 2, and tau 2 to 1. And we also observed that the SVM models with RBF kernel with these parameters performs the task for this scaling. And then the performance of this method is on the different data set is shown in this table. The error values we use mean absolute error for the accuracy and RMSE for the precision. We can see that the mean absolute error values is consistently below than the 0.06. This variation is okay, considered to be satisfactory for the purpose of measuring the structural similarity. Then, while looking at many tools that measure the software similarity, we do not find any that perform the structural we do not find any tool that performs the structural similarity. This we identified when doing the experimentation on the approach detection part. This is all about the program similarity part. Let me move on to the approach detection module. In the approach detection module, the main idea is to group the correct submissions, which is marked by the testing phase, into different groups according to their approach. Approach means the implementation strategy each students follow to implement the function. So here, the green colored nodes GS1, GS2, GSN are the correct gold standard solution, which means these are the solution marked as a completely correct solution by the testing phase. Then we fed this, we generate a graph to perform the approach detection task, then do the node clustering, and this will give us the different clusters. Each cluster members have the similar approach, cluster members which have uses a similar approach. So the graph generator is basically helps to identify the different approaches. So we first, the graph generator module generates a similarity graph. You can see here, this is the similarity graph. In nodes in the graph represents the gold standard solutions, and edges in the graph means the similarity score between the gold standard. Here we are using the structural similarity, and the edge weight represents the similarity score of the between the nodes. Okay, so we use the complete graph concept. The similarity graph is a weighted complete graph. So for the similarity, the graph generator phase is an expensive module because of the similarity computation part. For example, for an gold standard solutions, we need to perform n-choose to similarity computation. So this is an expensive process. So we are forced to reduce the size of the graph. So for reducing the graph size, we can use two different methods. One is reduce the number of nodes, or reduce the edges numbers, or reduce the both. So we have uses two methods. One is the concept of connected graph, which is nothing but take the subset of the similarity graph. In this connected subgraph concept, we retain all the nodes in the similarity graph and reduce the edge sets size. In the induced subgraph, we reduce the both. So we reduce both edges and nodes. So before selecting which method is suitable for performing the approach detection, we have defined an agreement, which is cluster agreement, which tells that the clusters that generated from the similarity graph should agree with, the clusters generated from the sampled graph should be agree with the clusters generated from the similarity graph. That means here C is the cluster which is generated from the similarity graph, original similarity graph, and C dash is the clusters that generated from the sampled graph. So this the cluster agreement tells that the C dash should is the number of clusters in the C dash should be equal to the number of the clusters in the original clusters, and also in for each node in the cluster Ci in C, there exists a node cluster Ci dash in C dash such that Ci dash should be the subset of Ci. So in this way, we can tell that if we use the sample graph for the approach detection phase, we are not miss any of the approaches. Okay, so first we experimented with the connected subgraph. Here we can see that we retain all the nodes in the original similarity graph, but reduce the edge size. But unfortunately, the performance of the connected graph is not that much good because it doesn't not able to find out all the approaches. So we move on to the induced subgraph concept. Here we generate the subgraph by selecting and the sample and some sample nodes from the original graph. Then perform the node clustering on this induced subgraph. Then we check for the cluster agreement. Here is the steps. First, we compute the clusters for the before finalizing the similarity graph size. We first experiment with what the size should be for the sample similarity graph. So the sampling comes in mind in because in mind, with the reason that for a particular programming question, we don't have large number of variations of the possible solutions. For example, for a particular problem statement, maximum they will have 10 variations of the same 10 variations of the solution approaches. So keeping that in mind, and we sampled. So we sampled the graph and randomly check the ki nodes from the original similarity graph and checks for and compute the clusters on that graph and check for the cluster agreement. This process is repeated for 5 times, and we select the sampled graph size as the smallest k, which agrees the cluster agreement. So for the node clustering part, this is for the node clustering part, we tried Leuvian and IPCA clustering, and we avoid the methods like spectral clustering, those methods which are uses the number of clusters as input, because we don't know before performing the approach detection, we don't know how many number of possible solutions are present in the solutions set. So we avoid such clustering methods. And in this experiments, we uses the similarity check. We use measure software similarity and gamma isomorphism as the similarity checking method. And we these are the data set which we use downloaded from the competitive programming website. Also, we use it from the programming language course. And we could see that the Leuvian and IPCA clustering result here, and the Leuvian is performed well for the finding the approaches, and we can see that also we can see that gamma performs well for this particular problem statement, and others most is performing well. That is because most is given the more accurate result on fairly large size programming problems, while gamma is performing well on small sized programs. That was the reason, and also this was the main motivation to find our own method to find the structural similarity. Okay. These are the results. Then in case of the program similarity, we tried only the Python programs. We explored only the Python programs AST and measured the programming similarity. So we can generalize this thing the same method to overall other languages by incorporating the universal ASTs. Then improve the method using, we tested only in a small sized data set. So we can improve the model using diversified data set and large number of data sets. Then these methods in the structural similarity that is helpful for finding the multiple solution approaches. So most of the automated evaluations are evaluating the programs based on a single reference solution. So if we automatically find out the different possible solution approaches, that can also be a reference solution, can be used as a reference solution for evaluating the program. So it helps to allow multiple solution approaches, and also able to identify the false negatives in the solution approaches. For example, in this was during the SAR's presentation, he mentioned about the increment and decrement. The students should use the increment and decrement function for solving that particular problem. So maybe the student, instead of using the increment and decrement function, they will directly use the operators or arithmetic expressions and perform the task. But when we are evaluating those programs based only on the test cases, without referring their code segments, they can pass the test cases, and that can be marked as a completely correct solution. But it is actually not a complete correct solution. It is a false negative case. So if we perform the approach detection, we could segregate each solutions based on their approach. Then we could easily find out such kind of false negatives.
Thank you, Nikhila. I'll just take 5 more minutes and briefly tell you about the other piece of work, which is on simulation-based clustering. So this particular piece of work was done with Kapil Kalra, our 2018 summer intern. And as you have seen from Nikhila's talk, node clustering is one of the important tasks that we do so that we can detect the approaches. So this particular piece of work, which is kind of a small piece of work, but it has got a slightly radical idea in it, and that's why we think it merits being discussed here. And it is that we thought that can we use some principles of physics to do clustering. And what we did was, I will just give you a very wish-wash description. What we did was we thought of each of these gold standard solutions which Nikhila was mentioning, or the programs, you can think of them, as particles, point particles, which have got some mass and some charge. Okay, and we put them, we suspended them in some sort of an n-dimensional universe and allowed them to reposition themselves in a simulation environment and see whether similar particles, by similar particles I mean particles which are programs which are similar to each other, and they have strong attraction between each other, and dissimilar ones are those which have got less attraction between each other, right? So we wanted to see if the idea of treating them as charged massive particles, point particles, suspended in some sort of a higher dimensional space, allows them to settle into what we typically understand as clusters in our computer science world. So we did that with small graphs and slightly larger graphs. And without going into too much of details, I will show you some pretty pictures, which are basically the results of all these simulations that we ran. So as you can see here, this blue graph shows the path or trajectory of the blue particles, and this is the trajectory of the green particles. It turns out that they all tend to accumulate or cluster at the same places. Okay, and this is again another graph, and what I will show you here is an increasingly complex set of graphs, and in each of these cases you will see that we were able to achieve clustering. Okay, there were cases where we were not able to achieve clustering, but there were not many of them. Most of them we were able to achieve clustering. To the extent that we were able to pursue this idea, it was very clear that the idea is not completely silly. It does have potential, and it is able to achieve clustering very similar to the clusters that our traditional clustering algorithms are able to do. The thing is, it's very expensive. The complexity increases exponentially with the number of dimensions, etc. So you may wonder why, what is the merit in having this particular approach. So our point of view here is that think of a slightly futuristic computational model where we do not really use a digital computer to do our simulation. Rather, we actually do a physics-based computer, which has real suspended particles. I cannot envisage such a device completely as of now, but in some foreseeable future, we can think of such a thing where the parallelism is natural. Okay, and if you think of parallelism as a natural part of the computational system, then this particular approach, if it works, will be far more scalable than our traditional computational approaches, because it is going to exploit the natural parallelism present in the computational model. And that is what you see happening here. So as you can see, so here is a graph which has a large number of nodes, I think about 300 of them. And what we have been able to show here is that they eventually go and cluster together after several tens of thousands of cycles of simulation. Okay, so right, so these are all the examples that I have got, and I think that's about it. So we were able to prove the concept. We did not get time to do any further experimentations, but enough to show the potential of this idea. So that's the last part of the talk, and this goes and fits well into the clustering part of our automated evaluation of programming assignment work, although looks like it's a very physics and clustering kind of work, but that's okay. That's the thing about particle simulation based node clustering. So let me wrap up at this point. So we presented to you our experience and the system architecture of an automated evaluation system, which we have designed and used in our case. And the objective of showing that is to encourage you to try it out on your end if you are an instructor of a programming course. And please provide feedback as to how you think it could be improved to make it more usable and effective. Apart from that, we discussed these 3 pieces of work, which are the research that we have done in the area of automated evaluation of programming assignment. And yeah, that's about it. That's the end of the talk. Thank you.
Yeah, thanks a lot, Sujit and Nikhila. So, are there any questions? Professor Prasanna has a few, which he has written in the chat box. If there are anybody else who would like to post their questions, you could unmute and ask, or you could post it in the chat window, and I can read it out for Sujit and Nikhila to answer.
Yes, Meenakshi, that would help.
Yeah, maybe while we're waiting for other questions, Professor Prasanna has several of them. Some of them are more like comments. So it was probably written in the context of the presentation at that point in time. At 2:17 p.m., he's asked this question about body language, handwritten scripts, and diagrams. I don't think they can be evaluated. And then the first question is, how difficult is it to check independent statement reordering, possibly across different methods, and with dummy code inserted in the middle?
Okay, I think that's a very pertinent question. The simple theoretical computer science answer is it is most likely undecidable, because we are talking about arbitrary permutations of instructions with arbitrary side effects on variable values, considering the fact that there could be loops involved, and the number of times we iterate may be dependent on parameters to the program. I think we can safely assume that it is an undecidable problem. In our case, I think the students are using some simplistic approach, which is obviously a heuristic and most likely going to err on the conservative side.
Yeah, I think the question specifically was across different methods. Because you
yes, that only complicates it further. I think even within a procedure, it can be proved to be undecidable.
Yeah. So there is one more question a little later, but I really don't understand. Professor Prasanna, if you are there, maybe you could add on to it. So the question reads as, have you tried YOLO, Y-O-L-O in capitals? type approaches to grab similar statements?
Prasanna, I am not aware of this term YOLO.
Yeah, hey, it's very simple. I don't know if you can hear me. The
Yes.
first is, yeah, I've just given some funny and half humorous things. Of course, body language, handwritten scripts and diagrams would be difficult. But suppose somebody just makes a simple two programs with each with 100 statements and simply permutes the statements mostly with independent variables. Is that a trivial thing to detect? That's not trivial unless you assume it's just permuted. The thing is, if you put dummy code in the middle, that's an easy thing to do, a dead code.
Right.
The last one is, I think YOLO may actually work because YOLO detects patterns. And YOLO actually, if you take, it will detect the same statement as long as it has image similarity. You may be able to, and it can, I think, even detect with proper configuration portions which are similar. Of course, this is NP hard and in fact undecidable and so on. But that theoretical perspective is not that relevant when you're talking of a few things in specific things.
Particularly for smaller programs, probably we can.
I think you may be able to do this with YOLO. In fact, we can talk about it offline.
Sure. Thank you, Prasanna, for the good input.
Okay.
Okay, so I had a couple of questions. So one is related to the last few points that Nikhila had made in her part about this essentially being tailored for a programming language like Python, and the point about generalizing it or extending it to other languages through AST. I didn't quite get that. How will just looking at the AST help to generalize it even to other similar programming languages?
Nikhila, you would like to take this?
Yeah, we could use the universal ASTs to handle the.
Provided the design is same, like for example, what works for Python may not work for Java, right?
No. It will work for the method is depends on the Python only because we have tried the Python API to generate AST. We have used. The method is work for other ASTs as well.
So one point I would like to bring up here is, in any particular scenario, we are always dealing with one particular programming language. So that is quite clear. We are not going to consider situations where we have to try and detect similarities between two programs written in two different programming languages.
No, that's not the point. But
right,
some other programming language.
Yes. So in any case, what we really need to do is to have a front end, a compiler front end, which compiles, which parses that particular programming language and gives us an AST. If we have, if we are able to translate this into the language of universal ASTs, then what happens is the remainder of the algorithms can work for all programming languages. That's the point. But if that is also not used, in my opinion at least, tweaking the algorithms for specific programming languages is not that fundamental a change to the programming language, to the algorithms, I'm sorry.
So the other question is related to, I mean, we know in general that any kind of, even the simplest kind of automated evaluation is an undecidable problem.
Yes.
Just to automatically check whether I can reach a particular program statement is undecidable. So you have tried it out on the experimental side. So is there any data point available on the accuracy of the results? Has it got the automated evaluation wrong? I will be surprised if it gets automated evaluation fully right for all programs submitted by the students, and there is no manual intervention that is needed at all.
So in most cases, we have got good results, and there have been cases where it has been off, but our evaluation is largely based upon the structural similarity, we also use testing, which is something that Nikhila had to skip. The overall architecture of the system also involves testing. So we actually do testing, and if we see that two programs are not matching in their outputs, even though their structural similarity seems to be matching, then it sort of raises a red flag, and it automatically either gets less weight, or it will be flagged up for manual intervention. So we use a mix of both testing as well as syntax or rather structural analysis.
Okay, yeah, sure, thanks. Any other questions from anybody in the participants? So if there are no more questions, let's thank the speakers, Sujit and Nikhila, and thanks everyone for joining.
Thank you for your attention. Thanks for the good questions and inputs.
Thank you, Meenakshi. Thank you, Sujit. Thank you, Nikhila, for the wonderful session. A big round of applause from all of us. And with that, we end the theme on education and technology. And we are all set for life sciences next week onwards on multiomics and data analysis in the area of multiomics. So with that, we'd like to close today's session. Thank you once again, everybody. Have a good day. Bye.
Yeah, thanks
Bye.
everyone.